The last topic in this section is partial differential equations. And I've got a partial differential equation up here on the board. This one is famous enough that it has a name. It's called Laplace's equation. And whenever we're working with differential equations, whether they're ordinary differential equations, those of you taking the differential equations class or who've taken it here at Saddleback, that's of course in ordinary differential equations. That's where we're looking at functions of one variable so that the only derivative is the full derivative. A partial differential equation would deal with a function of more than one variable so that there are partial derivatives involved. Okay. So here I can see that the thing I'm taking the partial derivatives of would be a function u. So we'd be looking for an unknown function u of xy. It would have to be of two variables here that would satisfy this condition, that the second partial with respect to x plus the second partial with respect to y, so the sum of the two non-mixed second partials is equal to 0. So any differential equation is always about looking for an unknown function so that the derivatives of that function, and sometimes the function itself will show up in the differential equation, but that those derivatives satisfy, the function and or its derivatives satisfy this equation. Now, actually finding such a function is kind of difficult. So all we're going to do with this is verify that a given function is a solution. Okay? So it's sort of like when you first started to learn algebra. If you had an equation like 2x plus 3 equals 5, at some point this might have seemed very intimidating because there was a letter in a math problem. Oh my goodness. And before you were given the instructions of solve this, you would be asked, is 2 a solution? So you would plug 2 in and you would be able to see, no, it is not. And then you would be asked, is 1 a solution? And you would plug in 1 and you would say, oh, yes, 1 is a solution. Okay, so that's the sort of thing you could be given. Is this particular function a solution? Or verify that a particular function is a solution. Let's phrase this one as a question. Let's look at e to the x times sine y. And let's see, is that a solution to this differential equation? Now, if I'm asked, is it a solution, I don't know that it's going to make the equation true. So what I like to do is just work with one side of the equation at a time. This equation has a left-hand side and a right-hand side. Obviously, the right-hand side is already fully simplified. It's just 0. But I'm going to just work out what the left-hand side is and then see, does it simplify to equal the right-hand side? Okay. All right. So if I were to take a look at the partial of u with respect to x, that would be e to the x times sine of y. I'm holding y constant, so y in any function of y is also just constant. And then if I take the second partial of u with respect to x again, I'm going to get exactly the same thing. Okay? Because if I took the derivative once and it didn't change, when I take the derivative again, it still doesn't change. Fascinating. All right, let's take the partial of u with respect to y. That would be e to the x times cosine of y. Now, e to the x is constant, but the derivative of sine y with respect to y would be cosine of y. And then if I take the second derivative with respect to y again, now I'm going to get negative e to the x. Times sine of y. Because, of course, the derivative of cosine y is negative sine y. Okay. So these are my two partials. So first of all, I just need to calculate them. Now I've got what I need to plug into the left-hand side. So the left-hand side was the partial squared u partial x squared plus the partial squared u partial y squared. That's going to be e to the x sine y minus e to the x sine y, which is 0, which is the right-hand side. So that tells us that this function, yes, it is a solution to this differential equation. Okay. Now, that's the sort of thing you'll be responsible for. Given a differential equation, I'm not going to ask you to go out and solve it, But I could give you a function and ask you, yes or no, is this a solution? And of course, you don't get any credit for the yes or the no. You would get credit for the work that demonstrated why your answer, yes or no, was correct. Okay. I will just mention, especially for those of you who are taking or have taken differential equations, there are a number of examples in the book, in the homework, of differential equations, and you might just be curious to sort of read through the homework, even if I didn't assign all of those problems, to just sort of get a sense of the sorts of partial differential equations that are out there. At the very end of this section, the last thing that the book talks about is deriving a differential equation that shows up in the financial world. Okay. Again, because this isn't a class in creating or solving differential equations, this is the extent of what you'll be responsible for, but some of you might be curious in understanding a little bit more about them, so I'd encourage you to read that last section, particularly if you're in differential equations or have taken it in the past, and you can just sort of see how similar this is to the differential equations that we solve in our class here at Saddleback, but that the key difference is that we're working with functions of multiple variables so that there are partial derivatives involved.